Hi there, I'm Kevin and I'd like to introduce to you Smart, an open source end-to-end system that allows practitioners to coordinate real robots at industrial scale and beyond. We're talking hundreds to thousands of them. Smart lets you instantly understand how planning algorithms perform outside the whiteboard, bridging the long-standing gap between theoretical multi-agent research and practical multi-robot deployments. Automation drives productivity. And in dozens of emerging industries, cooperative robots are performing all kinds of automated tasks, fulfilling orders, sorting mail, running errands, and so much more. Coordination at scale, so not just hundreds, but thousands of simultaneous robots, is vital for realizing the potential of current applications and unlocking the future potential of robotic automation. And every year, a wealth of new multi-agent planning algorithms are introduced from across different research communities. These ways compute high productivity solutions at industrial scale, and all of them promise to be applicable in practice. But the real world is messy, and these approaches, they almost never live up to their claims because they use simplified models and assume idealized execution. There's just no easy way to test the potential of planning algorithms currently, and to be confident that they work as well in real life as they do in paper. And researchers can only assume some robotics guy will adopt their methods and handle all the complexities to turn their idealized plans into efficient reality. So that's where we come in. We present Smart, an integrated open source framework that connects state-of-the-art multi-agent planners directly to robot execution environments. Smart consists of a comfortable web interface for uploading your plans and configuring problem instances, and instantly seeing them brought to life in a beautiful 3D simulation. Under the hood, Smart uses Argos, an industry-standard physics-based simulator, and an execution monitoring server that coordinates and monitors and distributes actions to each robot. Unlike existing toolchains that tend to focus on single robot or small team scenarios, we extend this to true multi-robot path planning. So up to thousands of robots, all physically simulated, visualized and benchmarked in one framework. Our system takes care of robot dynamics, ensuring your solution runs collision-free and deadlock-free. You can test any planner, any map, and instantly see how it runs in the real world. Our framework helps planning researchers by giving them a complete evaluation pipeline to measure the potential of their algorithms, from abstract models to messy reality. It also helps roboticists who can now access a wealth of planning technologies previously difficult to integrate into a feasible system. Let's get right into it. Grab your favorite multi-agent planner. If you already have one, perfect. If not, there are plenty of open source implementations to choose from. Export your plan in our simple text format. Each line is just agent ID, X, Y, and time. It's compatible with existing standards, human readable, and easy to generate from your code. Load that text file into our system. Our GUI will parse it and display the abstract multi-agent plan on your chosen map. Now press simulate and watch your plan come to life. Under the hood, we take your imported multi-agent plan and do a few things. Since the plan is a sequence of positions at discrete time steps, the robot can't use that as is. So we convert the plan into robot motions. We introduce new tiles into the sequence. We also account for gaps between the planning model and the physical model. So for example, robot dynamics and kinematics. Next, to ensure robots safely execute the given plan, our execution monitoring server builds an action dependency graph, which constrains actions to take place before or after certain other actions. This makes sure that robots cannot be desynchronized from each other. We then model the robots as real network devices that enqueue and execute actions received from the execution monitoring server via RPC. We simulate them in a physically accurate environment provided by Argos. Finally, the simulator communicates with our visualizer to let you play back execution, inspect individual robots, and analyze how your planner performs with physically accurate robots. If you're running locally, you can also use the standard visualizer that comes with Argos with the flip of the switch. Finally, the simulator communicates with our visualizer to monitor the whole simulation. The playback panel allows you to play back the execution and adjust the playing speed. You can also inspect individual robots by clicking on them, and the current progress of the chosen robot will be displayed on the dashboard, including physical state, action dependencies, and completion status. Our dashboard also collects metrics like sum of cost, make span, and average time to help you analyze how your planner performs with physically accurate robots.
We support custom grid-based maps, or try out one of our built-in examples to get a taste of how the simulator works.
We automatically infer dependency graphs, so who's blocking whom, and visualize these inter-robot dependencies. So here's one of the most powerful insights. You can directly compare the abstract plan's ideal metrics to what actually happens. Many planners look great on paper, but once you factor in execution delays, synchronization weights, and robot dynamics, the rankings can change drastically. Here's an example. Planner A is a state-of-the-art planner and is able to generate optimal multi-agent pathfinding plans. But it assumes that turnings are free, shown on the left. Planner B has a closer to reality robot model, which takes into account turning costs, shown on the right, and can compute optimal plans within that assumption. With the same map, they plan to take different paths. Planner A tends to navigate robots alongside obstacles as it thinks this is a better setup. Planner B prefers more straight movements, as turning takes time. Planner A has a better sum of cost reported. However, when considering the complexities of real life, it is not straightforward to compare which one is better. Now, load both of the results into Smart, and as you can see here, Planner B clearly progresses faster than Planner A. And at the end, the gap becomes really large. So this helps researchers analyze how much gain we can get from planning with realistic constraints, such as turnings. Next, we'll be adding more features to make the system even more configurable. Argos only provides the bare physical environment for the robots, so our architecture actually manages everything all the way down to the lowest level. We're talking everything from the data processing, networking between the central server and the robots, down to issuing wheel control commands on the robots themselves. No cheating allowed. So it pretty much means you can swap out Argos with real robots and would expect it to work exactly as simulated. At the moment, we have a fixed processing and execution pipeline. In the future, we'd like to support custom execution policies and components, as well as dynamic replanning and recomputations. This way, we can realize the full potential of its applications. In the end, it's about closing the loop. And with that foundation, we can then take on greater challenges and shape a smarter, more ambitious future.